Well, I'll list some examples for people who, if you just want a teaser of what's to come. Why is it that Heisenberg's uncertainty, or some analog of it, is already in classical mechanics under the proviso that you have to assume that thermodynamics is true? Another is that the action principle, which the way that I thought of it is it's a compression mechanism. So it encodes several different equations inside, and then you unpack it with Euler-Lagrange's equations. But you show the action principle itself has a geometric meaning. And the idea that you can translate between Newtonian mechanics and Hamiltonian mechanics and Lagrangian mechanics is false. You can't. There are some systems that are only describable in some, or not translatable to the other. There's not a one-to-one bijection between these guys.
Correct.
Okay. We'll also talk about what defines quantum mechanics. So many people think that it's commuting variables or non-commuting observables. Is that actually what defines quantum mechanics that makes it separate from classical mechanics? And why reductionism is incorrect. You have a video on, you shouldn't think physics is reductionistic, because at some point you get down to atomic facts.
At the fundamental level, like to justify the mathematical structure, you can't just say, oh, there is another mathematical structure that I use to justify this, because how would you justify the first?
And another way of saying that is that people think of physics as a mechanistic science, that you're always looking for mechanisms, but also that's another false view. I believe you say that because you can't look for a mechanism in something that's irreducible.
Right, because it's more that if you are at the fundamental level, you can't invoke a deeper level to justify the fundamental level that you have. There is no mechanisms after that.
That's a bit of a teaser. Some of those are technical. But why don't you go over the assumptions of physics project?
Right, so the project the goal of the project that I work on is essentially to find a minimal set of assumptions, physical assumptions, from which we can rederive the laws. And we have essentially two approaches. One we call reverse physics, that we start with the current laws of classical mechanics, quantum mechanics, and so on, which they're modern in modern theories are just presented as sort of a mathematical structure. And the idea is to go backwards from that mathematical structures and find physical conditions that are equivalent to that mathematical structure. And that's why it's called reverse physics, a little bit because it's like reverse engineering. You're taking the thing, breaking it apart, finding what pieces go together, what pieces are independent. And another reason is because in the foundations of mathematics, there is an approach called reverse mathematics that takes theorems and asks what is the minimal subsystem of mathematics that I need to express that theorem and prove it.
Now, just a moment. So in reverse mathematics, I've always wondered, so just for people who are tuning in, there's a theorem, and then you usually use assumptions to prove a theorem. And the way that I understand reverse mathematics is instead of starting from your axioms and moving forward to derive a theorem, you start with what could be true, and then you think about what needs to be true in order for that to be true.
Well, you're looking for subsystems. So to prove a simple theorem, you might not need, let's say, all of mathematics. You might need just a smaller subset of starting points, let's say. And you sort of, by doing that, you sort of learn more of what is the structure of mathematics itself. Now, I'm not an expert in this, but I actually had a chance to talk to one of the people that work there. And so what we do in assumptions of physics, in the reverse physics, is slightly different because we're more interested at the conceptual structure, like what is the minimal conceptual structure that I need to get to some parts of the mathematics of the physical laws. But the spirit is the same. You're taking what you think is physics, what you think is mathematics, and trying to find what pieces are there, like the structure of physics itself and mathematics itself. And one of the things that then we saw while doing this work is that you can have these physical assumptions that are equivalent to the different laws, but that sort of gives you only the higher level mathematical structure. And what we realized is that you really can't say that you understand the higher level mathematical structure if you really don't understand all the nuts and bolts of the more fundamental mathematical structures. And so we started another approach, which is called physical mathematics. And there the goal is really to start from scratch and layer in each axiom and definition, and each axiom and definition has to have a physical justification. So it's not enough to say, I have a mathematical structure. I have to say, these are the things that I have to model in the real world. And this is why I will use this particular mathematical structure to model this thing.
So why don't you give an example right now?
So, for example, the basic constituent that we use in physical mathematics, because we need a basic building block for everything, is the idea of a experimentally verifiable statement. A statement for which you have a test, and the test succeeds in finite time if and only if the statement is true. So, for example, you say the sky is blue, you can look, it's blue, finite time, verified. Something like the mass of the electron is less than 10 to the minus 13 electron volt. That's something where we can go and verify.
But a massless photon.
As another example, you can say the mass of the photon is less than 10 to the minus 13 electron volt, and that's something that we can verify experimentally. But if you said the mass of the photon is exactly 0, that's not something that we can verify experimentally because we always are bound to finite precision, right? And so these are the things that we want to have as a fundamental thing. We want to say a physical theory has to give us statements about the world, and a physical theory has to be fully explorable by testable statements. And so those are the things that we axiomatize. We say these things exist, and they have a particular way to be composed. So, for example, if you take two verifiable statements, right, you can verify the and, the conjunction, because you test one, you test the other, they both finish in finite time, then you know that the end finishes in finite time and it's verified. But if you have infinitely many, right, you're not gonna be able to be guaranteed because it would take you an infinite time to do it. So for a verifiable statement, you're only guaranteed that the finite conjunction is actually verifiable. You're not guaranteed the infinite conjunction. So the infinite conjunction is still a statement, but it's not a verifiable statement. And again, we have, in the justification, we have somewhat proofs that would have been accepted as proof probably in the 1700s, but they don't follow the current standard mathematical rigor, because mathematical rigor now starts with essentially elements that where the meaning has been stripped out is just symbols that you manipulate and so on. And when we're trying to reason on the physical objects, well, the physical objects are not meaningless marks on paper. And so we need to be able to reason what these things are, such that then we can find this definition and say, okay, these things can be. And so all of these processes we call physical mathematics, because at the end of the day, we will come from mathematics. We will have all the theorems, and we want to recover the mathematical structure that we already have. We don't want to create crazy mathematical structure that we don't know what they are.
You want to justify the use of the mathematical structures that we already use?
Correct. And find whether those are 100% appropriate for the type of physics that we're trying to describe, and what are what is the realm of applicability in those mathematical structures.
So something like the real numbers or even the complex numbers.
Correct.
Which are a continuum. Do they have a place in physical mathematics?
Yes. For example, we have a complete derivation, where we have a set of necessary and sufficient physical assumptions they have to make, such that a set of verifiable statements are going to be identifying with identifying essentially open sets of the real numbers. And so we know when we can take those things to be valid or not. And again, the idea is really to construct things that are modelization of what we do in sort of operational settings. So how do we define numbers? Well, we're going to have a reference, and then we say something is before the reference or after the reference. So for example, we have clock ticks, and then we say something happened, before the third ticks and after the second. Or you have rulers, and you have notches on the rulers, and you can say before this notch and after this notch. Or you have a balance scales, and you have weights that you put on one side, right? It always works like this. You have references, and the way that these references work is that essentially they give you three statements. Whatever you're measuring is before the reference, after the reference, or on the reference, in the sense that it overlaps. And the before and after are assumed to be verifiable. This is something that you can check. And now the question becomes, what is how many references do you need, and what is their logical relationship needs to be, such that all these references are going to tell you, aha, you're measuring something on a continuum of the real number. And what is most interesting in doing this work, apparently that it's fascinating because you really understand exactly how these things work. What we find is that there are three conditions that you need to have that are the most important, and it's like the biggest difficulty is not getting the real numbers. The biggest difficulty is to find a linear order. So a set of points that you always have something either before or after. That's really where all the sort of a harder assumption that you need to put are there. Once you have the linear order, whether you have the real numbers or the integer is just a matter of saying, oh, I have two references. Can I put one in the middle of the two?
Okay. Now, why is it difficult to have an order on the real numbers? Because they already are ordered.
Right. No, it's justifying an order with just saying, oh, I have these references where things can be before or after. Right. So references don't need to be ordered. You have references in space and you don't have a linear order there, right? And so the idea is that all the references have to be able to be arrangeable in some way such that, for example, if I put a reference and another reference, having something that is before this implies that something is before the other, right? Because the point is that you're starting from scratch. You just say, I have a bunch of statements. What are the minimal conditions that I have on those statements such that an order emerges from these statements? And that's the hard bit.
So what are you working on now?
What I'm working right now, it's sort of the piece that I need in between physical mathematics and reverse physics. I need
physical mathematics and reference physics.
And reverse physics.
Reverse physics, right.
Sorry. From the reverse physics side, right? I have a lot of conditions that allow me to recover fully classical mechanics and quantum mechanics, let's say, in a hodgy-podgy way that a physicist might like, but not a mathematician. And I need a place where I can run these arguments in a more precise way. And so I need sort of a general theory of states and processes that it's more abstract than the two theories, such as I can say, these are things that you always need to have if you're doing physics. You need to be able to define states, and states have to be to have these characteristics. And then if I have a classical system, I'm making this additional assumption. And if I have a quantum system, I'm making this other additional assumption. So I basically want to be able to push as much as I can theorems that are true both in classical mechanics and quantum mechanics, push them up to a single theory, right, to a more general theory, so that I can see these two other theories as instantiation of the two. And so again, this is part more of physical mathematics because I need to identify axioms that I have to assume to be able to do physics, in the same way that I say, well, physics is about experimental evidence, so I need to have statements out of the world that are testable. What I want to say is that physical theory has to be testable in a repeatable way, right? I need to be able to always set up experiments and test them. And so the basic objects that I have to describe a system must be at the level of ensemble. Because when I go and prepare things in a lab, that's what I prepare ensembles. I prepare statistical things that then I make statistical measurement, and it's on these statistical measurement that we have the inference.